All right, it's time, and it's the last class before Thanksgiving break. So, any questions from the homework? Okay, Nick?
5.2 number 17, please.
5.2. Oh, okay. Trying to do this. Okay, we are going to use the Riemann sum, where the sample points are chosen to be the right end point of each subsample. Okay. 0, 3. Okay, you divide it by n, so each part is 3 by n. Now what you have here is the first one is going to be 3 over n. The second one is going to be 3 times 2 over n, 3 times 3 over n. Every time you just add one more 3 over n. So for the ith interval, what you have is going to be 3 over n times I minus 1, 3 over n times I. And you're using the right end point. So finally, Rn equals sum I from 1 to n delta x times f 3n times I for your sample point. That's the setup. Go further, times, put in the function value. Now what we want is, sorry, it's going to be 1/4 x squared minus 6. Okay, which is, keep simplifying, n squared 9i squared minus 6. (27i squared over n cubed minus 18 over n). That will be the final thing. So now if we want to solve this, what we need to do is we need to take the sum and we need to use the formula Weber provided. So the first one is 27 over n cubed, 1 squared plus 2 squared plus 3 squared plus 4 squared. That's your I squared, which equals 27 n cubed. Now check Weber. They gave you the formula. 2n cubed plus 3n squared plus n divided by n, or divided by 6. That will be the first part. Okay. The second part, which is going to be 18 over n plus 18 over n plus 18 over n for n times. So together it's 18 over n times n, which is 18. Okay, so finally, limit n goes to infinity Rn equals limit n goes to infinity, we have two parts, 27 over n cubed times 6 over 2n cubed plus 3n squared plus n plus 18. Of course, this is 18. Of course, this is leading term. Everything else doesn't matter, so you have 9. Which is 27. Did I make a mistake somewhere? maybe. What did I miss? I missed a 4. And this should be a minus. Because this is minus. I copied the wrong thing. Okay, so if I have a 4, that's going to be different. That's going to be 4 over 9 minus 18. Negative 4, 72 minus 9, 63. Okay, that'll be right. So this is your Rn. And this is your final answer when you take n goes to infinity. Again, it's a long process. We want to do it again to show you the supreme performance of fundamental theorem of calculus. That is, just plug in ending points after you have found the antiderivative. So which is 12, 27 minus 18, which is 9 over 4 minus 18, which is negative 63 over 4. So again, this is way better than Riemann sum. All right. Any other questions? If no question, let's continue and finish the last part of 5.5. We did something called U-Substitution. Okay. The idea is quite straightforward. We want to simulate what we had for chain rule. So if you see some integration, okay, what we should do is we should first go ahead and try to realize, well, there is some function, and here is the derivative of the function. Once you have seen this, according to the chain rule, you can let u to be this one, and this one automatically will produce a du, which is the derivative, which will help you to cancel out this term, leaving you only u. So if you do that, you have this, then dx is going to be du over 3x squared. Now you take the original problem, you copy everything you can copy, you replace anything that you can replace with u and du. And because of your observation before, these two will definitely cancel each other because they come from the derivative. So finally, you have a totally new thing, which is basically the same as before, except for a change of variable. But now everything looks way easier. Okay, you don't have to worry about x cubed anymore. You just focus on the u part, the cosine part. You end up having 1/3 sine u plus a c. And finally, when you finish, you just plug everything back. Okay, that's the idea of u-sub. You do a change of variable. After you do the change of variable, the integral looks easier. Finish, and then change the variable back. Okay. The harder part is actually realize which one to assign to be u at the beginning. You have a lot of choices. But the key point here is you want to pick a u such that the derivative of the u you picked has already been prepared in the original question, like this case. If you pick u to be that, you need 3x squared, and x squared is already provided. With that in mind, now let's go into the second one. This is not easy. Okay, we need to do a lot of exercise in order to get familiar with it, and I prepared a worksheet for you. So let's first go over the last part of this section, and then we will start working on the worksheet in class today, and also after you come back from Thanksgiving. After that, you have 2 full class devoted into this exercise. You should be more or less okay with how to do U-Sub. It's not difficult, but it feels pretty strange at first. Now you just need to get familiar with it. All right. So the second thing we want to talk about is U-substitution. For definite integrals. And we will do it through an example. That is from 0 to 4, 3x minus 4, plus 4 dx. Now we have done this before. Before you do anything, forget about the ending points. Just go ahead and try to find the antiderivative. So do the indefinite integral first. Plug in 0 and 4 later. And to do this, we use U-Sub. Okay, these will be my rough work. I can see, well, if I have the square root of u, I'm going to have u to the 1/2. Therefore, if I take the antiderivative, I will have u to the 3/2. Okay. The rest will be just make sure that everything's well defined. That's a classic U-Sub. You see a dx, replace it by du over 3. So this is 1/3 square root of u du. 1/3 is not a problem at all. So take 1/3 out. You do want u to the 3/2, but in order to make sure it's well defined, you need times 2/3. Plus a c. Okay, that's a U-Sub. Once you finish, what is this if you put 4 and 0 back? Then you know, well, that's just (16) minus 4, which is a lot. 8. Okay, together it's 1, 2, 8 minus 16, which is 112 divided by 9. There's no way you can simplify anymore, so that's the easiest answer you can get. The simplistic answer you can get. Sounds good? Okay, that's how we do the U-Sub. First, get the antiderivative, change everything back to x, and then finally plug in a number. So if we write down the process, it's going to be starting from x, change everything to be u, finish, change everything back to x, use the ending points 4, 0. Ending points of x. It's not too bad. But now we want to make our life easier for definite integral. That is, we want to bypass these two. We don't want to do it. Okay. You already have everything in terms of u. Why don't you just finish the integral when you have u? You don't have to change it back to x. Sounds good? That's what we're trying to do. That means once you finish everything up to here, don't continue. Skip So skip everything that you need to change it back to x and then plug in. I just want to plug in the ending point right away. Not this one. Make sense so far? You already have a function, right? You already have the antiderivative. All you need to do is just plug in the ending points and done. So instead of changing everything back and plug in the ending points of x, how about we just plug in the ending point? But you see what I mean, right? You need to plug in the ending points for u, not for x. That means if x is from 0 to 4, you cannot simply just say, hey, my u is also from 0 to 4. That's not going to happen because you changed the variable. Okay. But you can plug it in for different numbers. And which number do you think? Well, if your x start from 0, what is your u? Your u is 3x plus 4. That means your u start from 3 times 0 plus 4, which is 4. So when your x is 0, my u is 4. You let x go from 0 to 4 is the same as let my u start from 4. Good so far? Similarly, your x ends at 4. What about your u? Then your u ends at 3 times 4 plus 4 at 16. So your x went from 0 to 4 is the same as my u went from 4 to 16. So I don't actually have to change it back to and use 0, 4. I can stay here, don't change back, but use 4 and 16 instead. Make sense here? Okay, that's what we're trying to do. You can go ahead and try to do it. The moment you start doing it, you realize that's the same as before. It's actually exactly the same as this line. So you basically, by doing this, you skipped everything from here all the way up to here. You bypassed it. Sounds good? Okay. The old way, of course, will work. This way is just simply better because it's shorter. I'm going to finish this. Okay, so that's the idea of doing U-substitution for definite integral. Since you're going to plug in the ending points either way, if you can, you have to change it back to x and plug in ending points for x. Why don't you just change the ending point from x to u and then finish there? Okay. I'm going to write down the formula, which really there's no point of reciting this one as long as you know what's going on. This is the chain rule, right? So basically, if you do a u sub, your u is going to be gx. Then this one tells you can change this to be fu du. It's just your ending point has to be changed to be the ending point for u. That's the formula you need. Okay, let's try to look at this example. Before we say let's just do this one first, forget about the ending point. This time I say no, keep the ending point. Okay, pick your u. If you pick your u to be this, you need a 3 minus 5x times negative 5, which you don't have here. Fine. If you let your u to be 3x, you need a derivative which is negative 5. It's a constant. Constant really doesn't matter because you can multiply a constant and divide by a constant. Therefore, probably this will be a good choice. Okay, du over dx, negative 5 dx equals du over negative 5. So the whole thing becomes this. Sounds good? Okay, that's U sub part. Finish. Okay. Now you realize the problem. Wait a second. 1 and 2 is for x. I'm doing the variable u. I should not use 1 and 2 anymore. Okay, I should change it. X, u is 3 minus 5x. If x start from 1, my u start from, which is negative 2. If my x ends at 2, my u ends at negative 7. So instead of this, I should do negative 5, negative 2, negative 7. Okay. Should I change this? Well, probably yes, right? Because I'm not doing x. If I put this here, I'm expecting everything here to be x. So actually, I should start changing it all the way from here. The moment you switch every x into u, your ending point also switch with it. Sounds good? The rest is super easy. Which is 1 over 14. Is the idea clear? You just go ahead and do U sub. Okay. Just one more side thing to remember. That is when you change x to u, you also change the ending point. The way to change the ending point is quite easy. You take your x starting point and try to find the starting point of u with the same x, and you do know u as a function of x. That's how you assign the u, right? So you can always compute what u is when x is 1 and 2. Try this one by yourself. All right. First, we need to realize, and then we have the original function. We also have the derivative. That's a hint. Your u should be ln x. Okay. Which is your u, times 1 over x, which is your du over dx, times dx. They cancel. U du, which is 1/2 u squared plus c. Now for definite integral, you just want the ending points. The rest, try to find ending points. 1 to e, then ln1 to ln e. ln1 is 0, ln e is 1, so does everything make sense here? I think you get the idea. Okay. So now for the rest of the class, please go to Canvas and click our class. And I already set up a worksheet. I should have. Ho-ho. Yeah, here. Which is called substitution. You just click it. And you will find a list of 11 problems. So please go ahead and try to do it in class. I will be here if you have any questions along the way. And also we will be doing this one when you come back from Thanksgiving. Okay, after 2 class time of in-class practice, I hope everything is okay. And of course, I will open the webwork for you too. All right, for the rest of the class, let's just do this.